All right, so I guess we will go ahead and get started. What's going on, Cantina family? I'm Fergie from the Cantina team, and today we have a super awesome one for you. We have Runtime Verification here up on the stage to do a quick workshop on how to make the most of their tool that makes auditing that much easier. Joining us today, as you can see, is Raul. He is the head of developer tooling over at Runtime. He uses his experience in auditing and formal verification to build the best security tooling out there. So without any further delay, I'm going to go ahead and pass it right over to Raul and let him do his thing.
Yeah, thank you very much, Fergie. And I'm really proud and excited to present to this awesome community. I think I've met some of you guys like in real life or at another workshop online, maybe. But if we haven't met yet, so let me just quickly introduce myself and the company I'm working for. Fergie just mentioned it. I'm Raul. I work for Runtime Verification. We are a security company, and we focus on formal verification and security tooling and developer tooling. So you may know us from our flagship tool that is Control and KEVM. So these are open source formal verification tools that we have been developing since 2019. And last year, we developed a new tool that's called Symbolic, and it's a Solidity debugger. And this will be the topic of today. So a little bit about my background. I joined the company in 2021. I also started as an auditor and formal verification engineer. And when I was doing my audits, I was a little bit underwhelmed by the availability of Solidity debuggers in this space. So I'm a very visual person, and I have a really short-term memory. I cannot keep up mentally. I cannot keep track of more than a handful of variables at any single point in time. So that's just where my brain is super bad at. So I figured, well, a Solidity debugger could solve this problem for me if I would just be able to step through my code and it would remember the variables for me. That would be the perfect tool that I needed to just, be more effective doing audits. And, no such tool existed or it didn't fit my needs. So that's why I started developing the Solidity debugger kind of as a side project at first. But then pretty quickly, I showed it to the company, and now we are doing it, developing it at Runtime Verification. So I'm going to spare you this slide. I know you are all security perps, so I don't need to remind you why security in the Web3 space in DeFi is important. You all know that. So that gives me a little bit more time to go really deep into Solidity. I expect, you are some giga brains. You know how Solidity works. You maybe know how the EVM works. So I will just try to do more demo time today than I usually do. So this is some stuff that I may want to show to you today. So I want to show you what happens exactly when a contract starts executing, not just on the Solidity level, but on the bytecode level. Like, how's your ABI encoding validated? How is the external functions that you're calling? How is it actually dispatched? How are Solidity variables laid out in memory and in storage and in call data? How does the call stack work? But all this is to say, this is not really. None of this is particularly important. I just want to show you the tools and how to use the tool so that you can use it effectively to dig deeper into Solidity yourself. Let's straight go to a demo. That's why we're here. If you want to follow along, you can, and you haven't installed the tool already on your local machine, then you can go to this website, beta.symbolic.runtimeverification.com. It launches a Visual Studio Code instance in your browser, and it contains some Solidity smart contracts that you can then start debugging right away without installing, setting up anything locally. And now I need to change my screen. I want to share something else. Let me just find the right button. All right. So I hope you can see my screen. Is the font size okay for everybody? Okay, if not, then just let me know. So this is a running example that I love to use. So obviously, the challenging part when presenting like a tool for Solidity development in such a workshop is, well, you have to balance it between simplicity and complexity. Obviously, we don't have the time here to also introduce Uniswap v4 or Lido, some complex DeFi protocol. An ERC20 token would probably be too simplistic for you guys. So I choose this constant product automated market maker as an example, which kind of, for me, it fits the sweet spot between complex enough to be sufficiently interesting, but not too complex so that we don't lose a lot of time explaining the protocol first. And I should mention that this protocol or this example contract is taken from Solidity by example, and I'm sure you all used it before. You've all seen it before. If not, no problem. So the contract itself is not really that interesting. The interesting part is obviously the tool. So this is a constant product automated market maker contract, or a DEX, decentralized exchange. And the two main entry points to this smart contract is one of the entry points is the swap function that allows the user to trade a token on this market. And the other important entry point function is the add liquidity function that allows the user to supply some reserves, add some liquidity to the market. Now, okay, that's a DEX. Now we want to see how this code actually executes in front of our eyes. We want to learn, okay, what happens if a user actually calls add liquidity function? What happens when a user calls the swap function? And as you all know, there's a bunch of steps that you have to run, usually manually, before you can actually see your code executing. So you have to compile your contracts, you have to deploy it. If your contract depends on other smart contracts like this one, you have to deploy the other contracts first or need to link to them. So here it's you need 2 additional ERC20 tokens that can be traded on the DEX. And then you need to probably mint some tokens to some test users and set up the deck correctly. And then finally you can send a add liquidity transaction and then maybe go to use a block explorer to see what's going on. So this is all very tedious manual work. And with Symbolic, we try to eliminate this manual work and automate it for you. So instead of running all these steps, compiling, deploying dependencies, minting tokens, etc., you would just have to write Solidity code. So there's no user interface here that lets you deploy a contract. Instead, what you do is you write a dedicated debugging contract that is a self-contained Solidity smart contract. So this is very much like a unit test that is automating all this stuff for you. So we have this debug CPM contract. If you know how Foundry tests work, then this is very similar and familiar to you. So we have a setup function that first deploys 2 ERC20 tokens. Actually, let me not just show you the code. Let's actually run it while I'm explaining it. So we have a setup function. You can see I started the debugger just by clicking this debug button. It automatically stops at the very first opcode before any of your code is executed. So I can now see, okay, what is the state of my contract? And you see all the addresses are currently, all the state variables here. They are initialized to the 0 address because that's how Solidity works. Now, the first step that we do is we deploy one ERC20 token, and I can actually now see, okay, I can actually see that the variable here is actually updated. The ERC20 contract is deployed. This is the eternal state. I deploy the next ERC20 token. Now I have the token pair that I want to debug, and I can create the DEX that I want to do, that I originally wanted to debug. So going to create the DEX. And now we also we have a fully deployed DEX with a fresh token pair. But I also need some contracts now to simulate user behavior. So the two primary roles that you can have on a DEX is you can have a liquidity provider and a swapper. So that's why I'm creating two more contracts here. We will go into them in a minute. So, but you can see I deployed two more contracts, and now I'm minting some initial tokens to Alice and Bob. So nothing really unexpected, very simple. This is just the setup. This is not calling the add liquidity function or the swap function yet. So let me do this. I'm going to terminate this debugging session, going to create another one. Let's first look at the liquidity function. Again, I'm going to jump right into the function. You can see now that my contract is already set up. So before we executed the debug add liquidity function, the setup function always gets executed first, just like in Foundry. So now I'm stopping at the first line of the add liquidity function, and it's calling this Alice contract. Let's see what this Alice contract is doing by just jumping into it. And what you can see is that it is approving the CP, the DEX, to pull in this amount of token A and this amount of token B. So this is just solidity pattern. You have to approve a smart contract before it can pull in your tokens, right? So this is what the liquidity provider contract is doing here. So, and finally, it's actually calling the add liquidity function of the DEX. And I'm going to jump into this function. And now this is really where the magic starts, where things get interesting. So let's pause here for a minute and look at the smart contract state. So we see that this market is currently illiquid. It has no reserves. They are both set to 0, and it has no shares. So everything is 0. And now Alice is the first user providing her liquidity to the market. So what the market now does, the first thing is it pulls in the token from Alice. So these are the first two lines here. I'm going to execute over them both. And now this brings me to some sanity check. So this sanity check is testing, hey, if we have some reserves, is the constant product automated market invariant holding? Like, is the constant product formula really holding? So, but because this market is not yet liquid, this check is skipped. So because it trivially holds at this point, everything is 0. Let's go to the next line. What it does now is it checks, hey, do I have any, do we have any shares minted yet? We don't. We can see total supply is 0 at this point in time. So we are going to jump into the Zen branch. And it's now calculating how many shares should be minted to Alice. And so this is an easy calculation. It's 100 times 100, and then taking the square root. So the amount of shares should be 100 that we get out. Let's confirm our hypothesis by jumping over it. And you can see that the variable shares, this is a local variable. No, this is not a local variable. This is actually a return variable from the function. So So shares is set to 100. That means that the next require clause check will also pass. Now we are actually minting the shares to Alice. So let's probably jump into the minting function just to show you some more functionality. So you can see it now automatically opened, jumped into the mint function. It's just updating the internal balance and then the total supply. So going to jump out of this function brings me back to the add liquidity function. Going to step over this brings me back to the entry point of our debugging session, to the debug add liquidity function. So and now I can see, okay, Alice was minted 100 shares, and I can now also see, okay, what's now the internal state of the DEX? So I can look at the constant product market maker. I can see, okay, it has 100 tokens 0, and it has 100 tokens 1, and then so 100 tokens of each pair, and then 100 shares. So yeah, I hope that you see how this is useful while auditing protocols. Just because, well, I mean, this is still a very simple smart contract. But you know, DeFi protocols, they can be incredibly complex. And these execution traces, they can get really long. So if we look at the next example, that is a swap operation instead of a liquidity function, then, well, there's already 10 times more variables to take into consideration. And at least I always found it really hard to to keep track of these variables manually. Actually, when I do audits, or when I did audits in the past, I actually started thinking of a scenario like, okay, what happens if a user adds liquidity to a DEX? Then I came up with some parameters that I considered interesting, and then I manually executed mentally and with pen and paper, I executed through the smart contract. And I was wasting so much paper. And this was really a dumb task because, well, all this bookkeeping of variables is something that is easily automated. This gives me, this frees my memory and this frees my mind to look at the high level picture of everything. I don't need to remember, okay, this reserve is updated in this particular way, and this is how the shares are computed. So I started with these parameters. So now this is how I calculate the shares. No, I don't need to do that anymore. I just execute it step by step. The debugger keeps track of all the variables, and I can see, okay, is this add liquidity function, is it following the intended behavior? Is there some edge cases? I can easily, the nice thing is now I have this boilerplate code written for this smart contract. So I can now see, if I wanted to know, okay, what happened if Alice did not provide 100 tokens of each token in the pair, but what if she provided like 150? What if she provided 110, 100 and 0? So this makes it very easy for me really to follow the execution path and see what's going on with different parameters. Okay, some more functions I will just let me just do a quick went you through some more features. So we have the going to call the debug swap function now. So of course, what you would expect from a debugger is the ability to set breakpoints, right? And I can do that. I can set a breakpoint in this line and start executing directly to this point, and it stops here. So breakpoints, standard debugging feature that you would expect. Also, well, we have call stacks. Like if your function is calling into another function, basically, whenever you call a function, a new stack frame is popped on the Solidity virtual machine, and then when you leave the function, the stack frame is popped again. So this also allows me, I just jumped into the add liquidity function, but I now want to see, okay, what happened before I called this function? What was the state of Solidity right before I entered this add liquidity function? And I can now go in my call stack, jump back and see, okay, this is where the call happened. This was the state of Solidity when this call was made. You can see there's some weirdness here in the call stack because, well, there's 2 frames actually recorded for each call. And, well, the short story behind this is we have to make a difference between Solidity call frames and EVM call frames. So Solidity is a language built on top of the EVM. The EVM has something that's called external calls, but Solidity also has like internal functions that don't generate a call frame on the EVM, but still Solidity has kind of an internal representation of call frames. So this is why you see 2 frames here for each function call. One is for the EVM level, one is for the Solidity level. Okay, so this is all nice and cool. So now let's go really deep because I know, well, you're Giga Chats. And let's go one level deeper. Let's look at, okay, let's say you want to learn, or you really want to look at how some specific feature is implemented in Solidity. Like, how does the generated bytecode look like? So I can do that. I can take any call frame, right-click, and open the disassembly view. And this will bring me, this will open a new view that is that's showing me the disassembled bytecode. So in this middle column here, you see the disassembled bytecode. I can see, okay, the debugger stopped at a dub run operation. So now looking at the bytecode itself is cool, but we also need to see the internals of the EVM state. And this is why I have this other scope here that I have not expanded before, but let me just collapse all the Solidity states. And now we are looking only at the EVM states. So I can see, I get now access to the low-level virtual machine state. I can see, okay, this is my core data. This is my program counter, 122 in hexadecimal. This is also where the cursor is pointing me to. I can see, hey, these are the contents of my stack. This is my memory. This is my storage. So these are the primary data locations for the EVM. Now, the EVM is a stack-based machine, so that means most of the operations, they will take their parameters from the stack and they will push their results back on the stack. So here's what happens if I execute over a dub run operation. And so dub run just duplicates the latest item on the stack. So in this case, it's the bottommost item on the stack. You see stack item number 4 is all zeros. Executing over this dub run will push another value on the stack that is all zeros. Now, push 0 is also just pushing all zeros to the stack. Now there's an sload operation that's maybe more interesting. So, but just what I want to show you is you can go really, really deep if you want to. You can see every single bit of the Ethereum virtual machine change. I can also set breakpoints directly at the Ethereum virtual machine level, so directly at some instructions. Oh, by the way, I didn't explain what is this leftmost column. Like the middle column here is the disassembled bytecode. The leftmost column is basically the address of the contract that we're executing and the program counter. So you have, because we need some way of uniquely addressing a bytecode instruction in the virtual machine, and there's not, well, one weird thing about the Ethereum virtual machine is that the bytecode that we're executing is part of the machine configuration. It lives in the accounts that we store on chain. So this is just a unique way of addressing code that we're executing. And essentially, it's the contract address and the bytecode. And then there's some bit here in between that is also signaling us, hey, is this executing creation bytecode or deployed bytecode? So it's an annoying representation. It's not very human-friendly, human-readable, but actually you don't need to care about it that much. The important thing is really just the disassembled bytecode. And the rightmost column here in this view is the war bytecode. If you like, push to operation is the hexadecimal code 661, and then the next 2 bytes are the parameters that we're giving to this push to operation. Yeah. Also, what else? I can look into the accounts. So we have a virtual testnet here, and I can inspect any address that is living in this virtual testnet. I can see, okay, 0 address has 0 balance, has 0 ease, non-zero, has no code, has no storage. Now, this address is more interesting. It seems to be there is some smart contract living on this address. So has balance 0, it has a nonce of 1, and then it has some code. So this is the deployed code that is living on this address. It also has storage, so I can really go and inspect any account that I want to that is living in my virtual testnet. Let me just, maybe just instead of just describing what we see here in the virtual machine view, let's maybe take some, let's maybe look at what happens if we start executing a smart contract. Like before, let's look at this debug CPMM contract first. Before we actually dig into, when we run this debug swap function, when we submit a transaction on the blockchain calling this debug swap function, there's some code that is executed before any of the code in my swap function is executed. So this is the code that is doing some basic input validation, and it's also the code that is dispatching the correct external function. So external functions are a concept that only exists at the Solidity level. At the EVM level, we don't have a notion of external functions. Like, we only have smart contracts, and they have a single entry point. They always start at the first opcode. So this is external functions and public functions is a concept that is only implemented in the Solidity compiler. So now let's see how this function dispatching logic is actually implemented. And I'm going to go back real quick to some slides, and then we will have another demo session in a couple of minutes. But I need to provide some theoretical background, otherwise it just won't make sense to you. Okay. Okay, I hope I'm sharing the presentation now. Contract initialization. So this is showing you basically the first 20 operations of almost every Solidity smart contract. They almost look all the same. And on the right-hand side, there's a small explanation on what this code is actually doing. So the first thing that Solidity always does is sets the free memory pointer. So this is just telling Solidity, hey, if you have a string or an array or anything that needs to be stored in memory that cannot be stored on the stack, then here's the location of the next free memory area. So this is what it always does, and it always sets this free memory pointer to hexadecimal value of 80. This is just a convention that Solidity uses because it uses the first 64 bytes as what it calls scratch space. Then there's the next 32 bytes are storing the free memory pointer, and then the next 32 bytes store a zero, just a plain zero that is used when we initialize new strings and stuff. Okay, this is the first three opcodes. Then, if you're calling a function, or if you have a smart contract that does not take any, does not accept any ETH with the transaction, then it's going to insert a runtime check here that the contract did not receive any value with it. And then it's making sure the next couple of bytes are making sure that the call data size, like the data that we received with our transaction, is at least 4 bytes. So this is also a Solidity convention. Every external function, every public function gets generated a function selector. This function selector is just the catcher cache of the function signature and then the first 4 bytes. So this is essentially just giving every external and public function an internal ID that is then used on the lower levels. So after these checks have been performed, the Solidity compiler then generates a dispatching table. So you can think of it, if you look at the bottom half of this slide, what the Solidity compiler does, it basically generates a huge if-else statement. And it compares the 4 bytes of the call data that it received to the function selectors of all the external and public functions. And when it detects a match, it will jump to the entry point to the bytecode that is responsible for handling the function body. Of course, this is still pseudocode, so there's nothing like an if-else on the EVM level. On the EVM level, we only have jump ifs. So this will look slightly different, but this is conceptually how it works, how Solidity selects the function. So here's how it actually looks in the bytecode. So the first 4 operations here, they are just loading the first 4 bytes of the call data. Essentially here is basically it's doing a call data load, and then it's doing a write shift so that only the first 4 bytes remain on the stack. So it then compares the first 4 bytes to the first selector. I think this is the selector of the debug swap function, and then the other one is the selector of the debug add liquidity function. I'm not sure about the order here. That's not important. But you can see, well, there will be 1, 2, 3, 4, 5. There will be 5 instructions generated for each function selector. And yeah. So now let's look at this in action. Looking at looking at bytecode is not very interesting. So going back to my demo. the font size is still okay. I accidentally resized this window quite some time. Okay, but let's just start the debug swap function. And the first thing I do now is I will open the disassembly view. And I can also put them below each other so you can see in the top view where we stopped in the solidity. In the bottom view, you can see where we stopped in the bytecode. So first 3 instructions is setting the free memory pointer. Let's actually look at the memory. Right now it's all zeros, so nothing shows here. Going to execute over the first 3 bytecodes. And now I see this is my free memory pointer. It's pointing to hexadecimal address 80. And the first 64 bytes here, they are the scratch space. So this is, if you're heavily optimizing Solidity code, then this is a section that you can use to for your own convenience. Like if you're writing Yule code or something like that, then you can use these first 64 bytes to do whatever you want. And I think you don't even need to clean it up. But you should also not expect that these bytes are cleaned up before you use it. Okay, so next thing that happened is contract validates that it did not receive any call value. So this check is going to pass. And now this is where our, oh no, that's not quite. So, okay, now we are validating that the call data that we received is at least 4 bytes. And I can see here, okay, my call data is exactly 4 bytes. So this check will also pass. So here I'm loading the call data size on the stack. Let's see. Okay, top item is 4. I'm now doing this comparison. Is it at least 4 bytes? And this check is passing. So now this is where actually the function dispatching logic happens. I'm loading the call data. Again, this is just the function selector. I'm making an equality check here. Let's see what's on the stack. So the first 2 items on the stack, they don't match. So I assume that this check will not pass. So now we need to compare it to different function selector. Now, okay, now we actually have a match. We have 2 times the same function selector on the stack. So the next jump I instruction that we see here is actually bringing us into the debug at liquidity or debug swap function. I forgot which one I have started debugging. Let's just see. Okay, and we can see that the Solidity cursor updated. We are actually now in the debug swap function, and we are now in the bytecode that belongs to the debug swap function. So this is Solidity function dispatching. Am I going too fast or too slow, or is there something maybe that the audience wants to see? I also asked a question on Twitter before, and some user, I'm not sure if he's here or she, but somebody wanted me to go over how dynamic bytes arrays are validated by the Solidity compiler. Is that something that you're interested in? Or we can maybe talk a little bit about memory layout.
Yeah, I think
Okay, somebody told me that would be cool.
Yeah, I think maybe it's a good time to see if you guys have any questions. Go ahead and throw them in the chat while Raul kind of brings it in. I think we have somewhere around 10, 15 minutes left on the calendar. So if you guys have any questions, comments, anything like that, pop them in. We'll get to those, maybe save like the last 5-10 minutes for answering some Q&As. So Raul, if you kind of want to maybe go into what that Twitter user had asked you, and then we'll kind of break into questions from the community here.
Yeah, let's do it real quick. I'll do a speed one now. So this is now getting really, really deep. And to be honest, I didn't know how the Solidity compiler generated these checks. So I had to come up with an example just before this call. So let's look at this debug call data contract that I have written. So basically, we have a contract called foo that is taking a dynamic bytes array as a parameter, and the data location is set to call data. So now the question was, okay, how does the Solidity compiler validate that the data here is actually valid and is well formed, so to say, because can throw anything in your call. The user is free to choose the call data, so you could provide us with garbage, and then the Solidity compiler should not just take this garbage as given and execute whatever it wants, but it should actually do some sanitization. So let's first look at what the call data looks like if we just call this function with some well-formed input. This is what this call with bytes array entry point here does. Am I showing the right screen? Yeah, I think you can see it. So I'm going to step into this function. Oh, this is the wrong debugging session. Okay. We are generating a dynamic bytes array in memory first. And so I should open this memory view. And now we are calling this foo function. And let me step into it. So let's look at the call data that we just received from this external call. The first 4 bytes here, again, are just the function selector of the with bytes array function. The next 32 bytes that we have here, they contain a pointer to the data area where this parameter is allocated in the call data. And this pointer, interesting enough, is not just an absolute offset, but it's a relative pointer that must be added to the offset of the memory. So we must add hexadecimal 20 to hexadecimal 4 to arrive at the data location of the of this parameter. So hexadecimal 20 plus hexadecimal 4 is hexadecimal 24. And now this is where the byte array starts, and the first 32 bytes here are storing the length of the bytes array. So I had 2 items in my array, 2 strings, hello and world. So this is the length of the bytes array. So now because bytes are once again, like the element type of this array is also a dynamic type, not some fixed size type. The next 2 call data slots will also not store directly the data, but they will again be once more pointers to the strings hello and world. So this is a pointer 40. Again, it's a relative pointer, so we must add it to 44. 44 plus 40 in hexadecimal is 84. This is giving me now the data area of where the hello string is allocated. So the length of the string is 5. Hello is 5 characters, and it's followed by the actual contents of the string. So we have now these bytes here. 68 is the ASCII representation of the small letter h. E is the ASCII representation. 65 is this ASCII representation of the small letter e, and so forth. And then So this is the pointer to the world string. This starts here. Length is, once again, it's 5, and then the data starts here. So this is taking me longer than expected, but basically what I wanted to show you is what I can do now to test the how the input sanitization works. I can assemble this call data myself manually in another function. So you see this block of code is just manually assembling the exact same call data that I have here on the left hand side. So, and then I could start changing bits of this call data, introducing errors, and just step through my bytecode and see where's the Solidity compiler inserting checks. So, for example, let me just take this and say, okay, the length of my array is not. This is what it was. It was 2. Let's say the length of my array is 10. So now I would expect that this call should revert because I'm not giving it a sufficient bytes. So let's see what happens if I call this function real quick. Okay, and it tells me, okay, hey, your transaction reverted, and I can now basically trace backwards how the Solidity compiler arrived at this revert statement, where's the input input validation actually happening. Okay, I see we have only like 10 more minutes on the clock, so I want to take the rest of the time for questions.
Absolutely. I think it's a great idea. So let's see. I know we got a couple here. We'll go back up. Let's see. Straponton said, "This looks awesome. Can't wait to try it out. Couldn't manage to get it tried on the link you shared. They said they were getting an error, and they also tried to join the Discord group. So could you just maybe one more time let everybody know where they can go to access the beta? I think you had a QR code somewhere, didn't you?
Yeah, I have a QR code. Let me just go back to showing the presentation. Wait. I have so many windows open on my screen. It's really hard to. I think I just closed the presentation, but I will just drop the link in the chat.
Okay. Cool. Yeah, I see Sil right here. I believe who's with the Runtime team said this should work and did drop in an invite. So there is an invite link in the stage chat if you guys want to join the Runtime Discord. Let's see. Perseverance Success 2021 asked you, can we use the tool for any setup? For example, I have a project with Foundry. Can I debug this with this tool?
Yeah, so actually Foundry is a hard requirement that we currently have. If you have a Hardhat project, then I have to apologize. This is not yet working with Hardhat. Your project must compile with Foundry. But then this is not... I think there's another question somewhere implicit in here, that is, can we use this tool to debug Foundry test cases? Because, well, you have to write all this boilerplate and setup code first. So, but you probably already have some unit tests or some fast tests using Foundry. Well, a Foundry setup is very similar to a symbolic setup. The difference is that Foundry also allows you to use cheat codes. And Symbolic does not support cheat codes. So if you want to prank a user, to impersonate a user, then this is not going to work. It will revert at some point. So yeah, you can use it to debug Foundry tests and Foundry code bases. Cheat codes are not working yet. We are working to get cheat codes implemented, but that's a different story on its own. It's actually really hard to implement this. We've been investing into this for quite some time, and it will take more time. So yeah, short answer, yeah, you can debug Foundry tests. Cheat codes, not yet.
Okay. And then we have Rebase who asked, are debugger commands available through command line similar to GDB or PDB, or are they only interfaced through the VS Code front end?
So, so we are building on the debug adapter protocol, which is an open protocol that kind of separates how the user interface works from the debugger process running in the background. And we are maintaining this free and open source Visual Studio Code extension that lets you connect to the debugger backend. There's other debuggers like Vim that have a generic implementation of the debug adapter protocol, so they might be able to connect to the server, but I haven't tried it out. And also, one-time verification is only focusing on the Visual Studio Code integration. But that said, if there's interest in developing a front end for some other editor, then well, we'll be happy to help out with that. It's just not our top priority. It's just informed by what most Solidity devs are using right now.
Okay. And then we have Alex the Entrepreneur who said, can you show us debugging a quick overflow or a rounding area, please? Error, excuse me. Can't talk today.
Oh, yeah, let me try. So let me. I'm super horrible at live coding. So wait 1 second. I need to share the white screen again. Oh, this is showing the wrong screen. Okay, so let's quickly just create a new function here. Function rounding error. I think I need an Solidity. Oh, do you want to see a rounding error or an arithmetic overflow? I just forgot.
He had asked for a rounding error.
For a rounding error. So, okay, let's see. UNT 256A is 3. UNT. Okay, this should be a rounding error. So this is dividing integer value 3 by 2. Because it's integer arithmetic, it's rounding towards 0. So C at the end should be 0. And I'm just going to insert another return statement here just to make sure that we can stop after we performed the execution. I don't want this disassembly view. Okay. So A is 3, B is 2. Performing this rounding division. C is 1. Oh yeah. Oh sorry. I'm too dumb to do math. Yeah, 3 divided by 2 in integer arithmetic is 1. Of course, not 0. I was doing the reverse operation. I was doing this in my head. See what this looks like. So this should give me 0, right? I hope so. Otherwise, I will make a fool of myself. This is giving me 0. So this is what a rounding error looks like. Yeah, it's really hard to spot. Like this is a rounding error. It's not giving you like it's not throwing an exception, right? Like it would do if you had some arithmetic overflow. And like also, if this is a rounding error or not, also kind of depends. Or if this is a security issue, like depends a lot on the context. It might be the correct thing to do here, actually, to round towards 0. It might be the wrong thing. Entirely depends on the application.
Okay, there we go. Let's see. Alex did post in chat a little code snippet and asked, could you then change the division to round up without needing to recompile? So I don't know if you want to take a stab at that. We have about 3 minutes left, so we are winding it down. So
Yeah.
up to you.
So, I mean, nothing is possible without, like, I cannot execute code without recompiling it, right? I need to at least compile it once. I mean, there's well, some debuggers of other programming languages, they allow you to evaluate some expressions in a paused virtual machine state. So basically, they give you a debug console, and then they are able to evaluate expressions like in a read evil print loop. This is not supported yet. It's super difficult to implement. I know that I think the Tenderly debugger just added a mode where they can do that. Symbolic cannot do it. So you always need to recompile if you want to evaluate a new expression.
Okay, awesome. Well, Raul, thank you again for coming and hanging out with us today. It was super exciting to see what you guys are building out and super exciting to see where you're going from here. One more time, what's the website where people can go to access the beta?
So you can download this extension from the Visual Studio Code Marketplace or from the VSX registry if you're on the open source side of things. This link that I just dropped in the chat, this gives you basically a full functional demo with the code that I used during this workshop, where you can try it out without installing anything locally. So, but I definitely encourage you, use it locally, run it on your own code. If it's not working as expected, well, just let us know. So this is still very early in development, so there's a very good likelihood that there's bugs. Yeah, and well, I hope you all are preparing for the Euler contest, and yeah, we will make sure that this debugger is working with the next big contests that are coming up on Cantina.
Awesome. Well, Raul, thank you once again. And for those of you that are interested, we did Sil posted a Discord invite to the Runtime Verification Discord where they have a dedicated symbolic channel. And then again, beta.symbolic.runtimeverification.com if you want to access this or just download it straight through the Visual Studio Marketplace. Other than that, Raul, thank you so much. And we will see you guys next time. It's been a pleasure, Raul.
Thanks for having me, Fergie. Bye-bye.
Bye-bye.